Right, so today what we want to talk about is explain a little bit about why we need quantum computing, some of the imperatives that are driving it forward. We want to then introduce you a little bit to the quantum physics aspects that make quantum computing possible. And hello, Matt. And a part of that is you need to kind of suspend your belief in certain things, and I would say, like me, take the engineering approach. Don't necessarily try and understand it in too much detail, but accept it for what it is, because then we'll go on to talk about how we use those quantum principles to actually do some computing. Now, having done that, what we then need to talk about is cryptography, because unfortunately, if it all does work, as it will, you're going to find that this is a bit of a problem for some of the modern cryptography that we've got out there. And we wanted to take you through one particular aspect, which a number of you probably have heard of already, called Shor's algorithm. Very much misunderstood, but Shor's algorithm is the reason why things like RSA, DSA, all the things you use today and rely upon will no longer be of any use. However, we're going to start with a warning from history, which is that some of this is prediction, and predictions in technology are fraught. I imagine myself in 50 years' time being this gentleman from 1950 at the Rand Corporation who's trying to explain what home computers would be like. Now, actually, all the components are there, except I want somebody to tell me what that big wheel was for, because I just no idea what that was for. So take all this in the right context. So if you all know something about computers, you'll recognize these classic logic gates. And this is what modern computing is all based on. Take an OR gate, so two inputs. Either one of those inputs is a 1, the output will be a 1. So 1 or the other is 1, the output. The thing to recognize on this is it's irreversible. So once you've got the answer out of the logic gate, you can't reconstruct what the input was. That's all I'm asking you to remember on that slide. And the reason that computing took off is because initially, obviously, these were invented, and in the Second World War, Tommy Flowers put these all together for Colossus, and then the Americans took it and built ENIAC, and they now have the industry and we don't, even though we came up with it. But small problems with this, like it used to take 150 kilowatts to run it and a small army of people. But these guys then came along from the Bell Labs, produced the first transistor, and everything started to miniaturize. We realized we could put the logic gates on single chips. I don't know if anybody's old enough to actually have played with these. I did when I was at school. And then, of course, we realized we could put all those together, make multipliers, adders, all sorts of other things, instruction sets, and the first microprocessor was born. Anybody here old enough to remember the 4004? I've actually used one. Yeah, oh, yes, good, good. There are some people around. Now, 4004, as it was miniaturized, this, by the way, this mask, the thing that fascinates me about this mask that was produced, this was produced by hand. It was the last one that ever was, but the big thing is the next few slides are going to go very quickly because the thing to watch is the numbers in red up there. So the first one was only 2,300 transistors. But obviously, very quickly, they were doubled and trebled, quadrupled, and all the way through to the Pentiums, etc. We just got more and more and more. And of course, a lot of you will already be aware of Gordon Moore's law, the man who founded Intel, or one of them that founded Intel, where he talked about the amount of number of transistors you could get in that given space would double every 18 months. Actually, that's a slide from his paper back in the 50s. He was wrong. He actually reckoned it would go on for 10 years. As it's happened, it's gone on right to the modern day. And if you look, there's a really good correlation, straight line all the way straight through the middle of that. However, as that great philosopher Scotty said, you can't break the laws of physics. We are coming smashing up against a wall at the moment, and although we're kind of still making some progress, things are slowing down because as you make those transistors smaller and smaller, obviously that's just cross-section through them. You're going smaller and smaller and smaller, and guess what? You eventually run down to the point where they're so small that you get quantum effects. The most deadly for a transistor, I think, called quantum tunneling. So you get the electrons, instead of acting as a switch, they can just spontaneously be on either side of the junction. So that causes the thing to fail. And we think, we're not absolutely sure, if I were a betting man, I'd say 5 nanometers is about the limit. Currently we're at 7. But really by 2020, we think we're probably going to be at the limit of producing these. So we need something new. I have to say it on several pages because I've gone on various slides. We need something new. And there are people trying to beat it. you get people trying to produce ultra-dense chips, etc. But frankly, this isn't the real problem, because I am old enough to remember working on parallel computing. I worked on a thing called the transputer many years ago, which allows you to do things in parallel, programming languages like Occam. So actually, although you might not be able to squeeze any more onto the same little chip, you can just put more chips, you can just have more processors. And indeed, last week, MIT came out with a new language, PhD student, in fact, came out with a new language called Milk, which is all about making it more efficient for data processing to be done on multi-core processors. So we're getting improvements, but not necessarily by putting more onto the chip. The real problem, however, is really this. It's algorithms. Now, if you're a baby computer scientist, you get taught how to do algorithms like, I'm sure if you are a computer scientist, you'll remember doing your first sort algorithms. You get taught bubble sorts, fast sorts, etc. But there are some problems that can't be solved and just never will be solved. And I'll give you a really good example, which most people, again, will have heard about, the travelling salesman problem. Let's pick 7 cities around the UK. Let's suppose we start up in Dundee, and it's about what's the optimal route around all of those? I did a quick sum based on the sorts of algorithms we do have available for solving that. There's obviously the brute force one. You just try out all the possible solutions. We have developed some algorithms, root and branch algorithms, nearest neighbor algorithms, which actually comes back to haunt you again in what's called shortest vector problem in cryptography. But the bottom line is, if you actually look at how long it takes, take a simple 1 gigahertz computer, obviously I'm simplifying, 14 cities, not going to take you too long. 22 cities, it takes you a long time. You only need to get to 28 cities, and it's going to take you longer than the age of the universe. There are just some problems that are speed up exponentially with the amount of data that you're trying to process. And that is our fundamental problem. And I've borrowed a slide from Scott Aronson here, he knows I have, which is that in complexity theory in computing, what you look at are what's called problems in Pspace. So these are things that can be solved in polynomial time, i.e. time that you can actually live through, or there's non-polynomial time, things that are just not going to be able to compute in, like those traveling salesman problems. So, for example, the traveling salesman problem will probably sit somewhere in the MP things. There are a set of problems that you can verify. If you've got the answer, you can verify that the answer is correct within polynomial time, but you can't get the answer in polynomial time. But there's also a series of problems that came from the physicists, where they said, we want to simulate quantum systems. This is back in the 80s, and they said, look, we've got all this fantastic information coming and all these theories. We want to be able to simulate these quantum systems and see if any of this is true. But when they started looking at the algorithms that they would need to develop, then none of them would really run in polynomial time on classical computers. And it was that point that Richard Feynman, he said, well, maybe we could use quantum mechanics itself to actually simulate bigger quantum systems. And then the light bulb went on. There was a guy called David Deutsch, there is a guy called David Deutsch, who's still visiting professor down at Oxford, I believe. And he wrote a paper, which I think will become the paper, rather like Turing's paper in the 1930s, which is seen as sort of the progenitor of all modern computing. I think his paper will be seen as the archetypal, this is how we produce what he called a quantum Turing machine. So his was the blueprint for how you do quantum computing. Now, to understand how you do that quantum computing, I need to introduce you to 3 quantum principles: superposition, uncertainty, and entanglement. There you go. That's it described in one sentence, or one equation. Now, it doesn't matter what that says. Forget that. If you're not into maths, forget it. The only thing you need to really concentrate on here is, see that funny little phi symbol, the trident there? That comes about, and this whole equation cannot be derived. Schrödinger, when he came up with this equation, it can't be derived. There's a lot of intuition in it. It's rather like Newton's second law of motion, F equals ma. You can only prove it by experimentation. But what Schrödinger said was, he believed that energy and momentum had some kind of wave-like properties. It propagated as some sort of wave-like entity. And that's really how he came up with this. So just remember waves. And if you go back to your school experiments. A number of people have probably done this experiment. Take a monochromatic form of light, put two slits in front of it, and what happens is you get two sets of waves coming out which interfere with each other. Trough meets crest, cancels each other out, crest meets crest, you get a bright spot. Yep, everybody done that sort of experiment at school? Some people do it with water waves, etc. Fairly simple. So, let's suppose we were going to fire individual electrons instead of light through there. Electrons are known to be particles. So, what would happen if you had a whole bucket of particles, bucket of sand, and you poured it through those two slits? What would you get? You'd basically get a distribution like that, two humps. Yeah? Make sense so far? And indeed, if you have one slit open and you what you get is one hump. The trouble is, when you open two slits, you don't get two humps. You get an interference pattern, which kind of doesn't make sense if these are particles. So one of the early conclusions of quantum physics was obviously that things like electrons, things as small as electrons, but things all the way up to Buckminster Fullerene molecules, C60, they all have a quantum property. They were somehow acting as interfering waves. And a lot of people for a long time, they looked at this and said, well, the electrons are all going through together. Yeah, maybe they're traveling as waves and each, different electrons are interfering with each other somehow. And there are still people today, although nobody's ever found it, who believe in the hidden force principle. They think there's a hidden parameter in here, a hidden variable. And in fact, Einstein never accepted this. He always believed there was some sort of hidden variable here. But it gets even weirder because if you start firing individual electrons through these two holes, and you give it enough time that they can't possibly interfere with each other, so they're going doing, doing, they're being detected at the other end as particles. You can see them appearing on the light sheet as individual particles. But as you continue over the hours, and you do this experiment over many, many hours, you find that the pattern that builds up is an interference pattern, which just doesn't make sense, because what it actually fundamentally means is every individual electron is interfering with itself somehow. Either that or time doesn't exist. I think most people think the former. So we somehow have electrons that are interfering with themselves. So one electron at a time is going through, it's interfering with itself, and these basically are the result of the fact that little phi symbol, what that turns out to be, it's worth saying, I don't think Schrödinger actually knew what it was in the early days, but the interpretation of it now is probability waves. So it sounds a bit like something out of Hitchhiker's Guide to the Galaxy, but matter travels as a probability wave. So the probability of finding those electrons at any particular point, the probability wave interferes with itself because it has a multiple number of probabilities. The solution to, oops, wrong one. Can I go back up? No, sorry. The solution to Schrödinger's equation, there are multiple solutions to Schrödinger's. That phi symbol, it turns out that there are many, many different possible solutions to it. Think of it the way to think of it perhaps is that the electron can go through multiple paths. There are all sorts of possibilities. Before it heads off, there's all sorts of possibilities. And because it's actually interfering, we can show it's interfering with itself. The conclusion was that actually, before you measure it, before it hits that screen at the other end, it is actually in all those states at once. So a single particle, single electron, that wave function, that total wave function phi, is actually a superposition, that's what the mathematicians call a superposition, of lots of different solutions. So, and anybody that study maths, you very quickly understand that anything that's a linear solution, linear equation, like Schrödinger's equation is, then any solution to it, there's another solution which is a combination, some combination of those individual solutions. And those little variables C there were called probability amplitudes. Basically, it doesn't mean anything at all. Nobody knows what it means. It was called probability amplitude because they knew it was something to do with probability, but they didn't really know what. It turns out if you take the modulus squared, that is the probability of you finding in a certain place. So modulus of C1 squared, modulus C2 squared, for example, they have to add up to 1. You have to find it somewhere, probability of 1 of finding it somewhere, but where, you don't know until you measure it. So that's where superposition comes from. Think of it as if you've got a quantum property of something, it can have all those properties at once, right up to the point where you measure it. And going back to what you might think of as the measurement problem again, if you redo this experiment and you put a little monitoring device behind the slits so that you know which slit it goes through, so it hasn't been measured over here yet, it's just a little monitoring device saying, I know which slit it went through, it turns out that you get two humps again. It doesn't interfere with itself. So as soon as the universe knows what state that electron's in, it can no longer interfere with itself, and you get what you think of as the particle result. And that's called dropping out of superposition. It turns out, unfortunately, for building a quantum computer, that dropping out of superposition is very easy to do. And so a lot of the work, a lot of the engineering that's gone on over the last 30 years has been all about trying to prevent things drop out of superposition so that they stay in that superposition state where there are all these possible values, all these possible solutions at once. The thing that nobody's ever been able to explain to me, though, is if you somehow randomly turn that monitor off, i.e. the experiment doesn't know, the universe doesn't know, this is analogous to Schrödinger's cat, if anybody's heard of this, it will know. Those electrons know. Somehow they know. And nobody's ever really been able to work that out. There's also a really weird thing called the delayed quantum eraser, where apparently it must have known before it left the electron gun whether you were going to turn it on or not, and that just gets plain weird, so I leave that alone. We then come to, I've called it Heisenberg's uncertainty principle, but really this is the measurement problem. And this is the fact, this is all to do with superposition again. This is the fact that, this is the fact that as soon as you know one thing about that particle, so it's traveling as a probability wave, and there are two things you can know, its position and its momentum. In fact, if you live in a Newtonian world, F equals ma, you can say, I know for definite what its position and what its momentum is, and indeed you can predict it all the way forward. You can't do that in the quantum world. Once you get to the point where it really is acting like a quantum particle, it doesn't do that anymore. And indeed, because it's simple wave mechanics, as it happens, it's nothing to do with quantum physics specifically, but if you've got a wave, if something's propagating like a wave, if you know its position very accurately, you don't know its momentum. If you know its momentum, you don't know its position. So you can never know two things about it. The big thing is that as soon as you measure it, as soon as you get an answer from it, it will adopt that answer. It will drop out of superposition, and you can only know that one thing about it. So if there were two possible things you could know about it, you will never be able to measure the two possible answers. And that's something I think a lot of people misunderstand about quantum computing. You might be able to do a lot of different things at once, but you can only get one answer out at any one time. There's then another thing that there's a lot of debate about whether this is actually needed in all quantum computers or not, called entanglement. And you might have heard about the Chinese quantum satellite that went up recently. I don't know if anybody saw that story, but they're using quantum entanglement for a form of encryption. And basically, this is, if you've got, say, an electron, and it's got its quantum property, if you entangle two of those together, and you separate them, take them to the other side of the universe, and you change the state of one, instantly the other will change. So they remain entangled. Their quantum fates remain entangled, always. Right up to the point where they're measured and they drop out of superposition. And that's really how quantum registers all work together. Very difficult to do because, as I said, you get all sorts of spurious things coming in from the environment that can cause things to drop out of superposition. But that's exactly what the Chinese are doing at the moment, where they've got, in fact, photons they're using, entangled photons. You send these photons to different places, you change one, you know what the other one is. Now, I hear you cry. But that breaks the laws of physics because how can two things communicate instantaneously without breaking the speed of light? Well, you'll have to trust me on this one. It does work. It really does work, and there's a whole theory, but there's a whole lecture that a thing called Bell's inequality proves that it does actually work, because you're not actually transmitting any information. Because when you measure one, let's take a coin. It could be heads or tails. When you measure it, it's randomly heads or tails. The other side simply know what you've measured. You're not actually you can't use it to say, right, I'm going to make it heads now, so you know yours is tails. You can't transmit information, so you can't break the speed of light from that perspective. But their quantum fates are definitely entangled, and they remain so. So, quick recap. Superposition. Things can be more than one thing at once until they drop out of superposition. Uncertainty, as soon as you measure it, you can know one thing, but uncertainty means you can't know lots of things. You certainly can't know more than one thing to any degree of accuracy. And entanglement, which is where if you've got more than one quantum item, its quantum state is bound to that of another. Everybody still with me? Boo. Okay. Right, so you're all now experts on quantum physics. As I said, you could spend hours arguing about what a lot of this means, and in fact, David Deutsch is one of the proponents of the multi-worlds theory about electrons interfering with themselves. I class myself as an engineer. I don't bother about that. I just say, what can I do with that? Right, there's some really interesting phenomena. What can we do about that? So how do you actually take all of that and compute? Well, this is where the qubit, you've all heard of bits. Well, there's the qubit, the quantum bit. And what you do is you pick something that has a quantum state with two possible values. And you say, right, I know how to compute using bits, using ones and zeros. But if I can create this qubit, it can be both a 1 and a 0 at the same time. And it turns out that there are a whole series of things like that. Take the electrons we were just talking about. Electrons have a property called spin. It's either up or it's down. It has only two possible values. We've known since 1922, Stern and Gerlach did their experiment, that there's only two possible values, and you can use that as your qubits. And if you have more than one electron together, you can start to build these registers up. So imagine a photon, or even something like an energy level. One of the things we'll talk about in a minute, a form of quantum computing is energy levels, where it has only two possible energy levels, and you have it in one or the other state. You don't know till you measure it, but it can be in both at once. And the big thing is, if you've got something like a register that's a 2-qubit register, you can imagine in a conventional computer it has four possible values, 0, 0, 0, 1, 1, 0, 1, 1. But of course the big thing is you can only do those one at a time in a conventional computer. In a quantum computer, they can exist simultaneously. And this is what a lot of people will think of, and they certainly talk about this, as quantum parallelism. So imagine all those values being operated on with the same function, but in parallel. There is a misconception, which we'll come back to. So all these things can be operated on in parallel, and you can see very quickly that the more qubits you put together, suddenly you've got a power law there, and you get more and more and more values, just as you do in a conventional computer, but all available at once. Yep. So the big trick is to get lots of qubits together. And it turns out, going back to those logic functions we were talking about, logic gates we were talking about before, there's a direct analogy with qubits as there are with bits. You've got bits are 0 and 1, there are logical operations, which are the gates. I mean, I put an XOR gate up because cryptographers like me love XOR gates. And you can build your truth tables up. So depending on your two inputs, you get your output. You know what it's going to be. But that side is deterministic. You know exactly what you're going to get. This side, the qubits, the way you operate on it is what's called unitary operators, unitary operations, which the best way to think of it is matrix maths. That's all it really is matrix maths. And you can create gates. Just in the same way you can with logic gates, you can create quantum gates. That's called a C-not controlled NOT gate. I'll come back to the gates in a second. But the qubit itself up there, you see the little equation? That's how we tend to represent the starting position of a qubit, 0 or 1. That just means it's 0, 1 or 1, 0 at its starting position. And then you put it into superposition. So if you can somehow get it into superposition, it's then a combination of both 0 and 1. And the alpha and the beta are back to those probability amplitudes again. That gives you the probability. Any one point in time, it gives you the probability that if you measured it right then, it would be 0 or 1. Yep. So if we go back to the sorts of gates we build into quantum computers, what happens? The simplest, and you'll hear this all over the shop, it's called a Hadamard gate. And this is what you actually use to put the thing into superposition. It's also called the square root of NOT gate, because if you put two together, it comes back out of superposition, and it's always the opposite value. So, but that appears everywhere. That's how you put the things into superposition. There's then the controlled NOT gate. You have one qubit controlling another qubit. And again, simple truth tables, just like you see in normal logic, and you can start to build multipliers. But imagine now, this is a multiplier where you can, if you were going to multiply numbers, and you wanted all the possible values from 0 to 100 multiplied with all the values 0 to 100, imagine being able to do that in parallel. So you can start to see perhaps where some of the speed comes from. Now, this is what's called the controlled NOT gate. The reason this is particularly important, if you get into quantum computing, is it's the universal gate. It's a bit like the NAND gate in conventional computing. You can build any other gate out of this. So that's the reason you'll hear lots of people talk about controlled NOT gates, CCN gates, and that's because you can build everything else out of it. Yep, so that's that. And there's a whole library of these gates. The Pauli gates, the rotation gates, the phase rotation gates, the identity gate, which does nothing, the controlled NOT gate, etc., etc. And all I've put up here is you can see, this is just for 2 qubits together on the right-hand side, but you can see what happens with that matrix. Basically, what you're doing is you're just multiplying the numbers by that matrix. So you don't really need to think about it in any sort of abstract way. If you're a mathematician, it's really very simple. And there are languages as well, specifically being developed. There are some which are more like assembler language, QSAM, Quasm. There's Quipper, and there's others that are coming out. I've forgotten the latest one that just came out a couple of weeks ago. But high-level languages all coming out, all aimed at being able to utilize these gates. So they're specifically written to put these gates in place. So you specify, right, I want a Hadamard gate now, I want a controlled NOT gate, I want a controlled NOT gate here, etc. So the theory is actually really well advanced. There's a lot of theory on quantum information processing, but there's a glaring problem with it, which is we haven't actually got one yet. So back many, many years ago, they decided, well, we need to get some sort of structure into this whole thinking process. And De Vincenzo, who's still at IBM, I think, he came up with a set of criteria. And there are a whole series of possible technologies that could be used. They do have these potential to give you qubits. I shall pick just a couple. The one I would keep, I haven't talked about it today, but the one I'm getting particularly keen on, and I have to say it's making my head hurt quite a lot, is topological quantum computing. That uses a thing called the mathematics of knots. And the knot mathematics, as in K-N-O-T mathematics, is bizarre. And I had dismissed that for a long time because it relies upon a mythical particle called the anion, which is a two-dimensional quasar particle. But suddenly in Holland, somebody's actually discovered that this might well exist. So, and they might be able to use it. So there's something to be said for that one. So of all the ones on here, don't rule anything out. Quick diversion, you may read in the press that you can already buy a quantum computer. You can go to this company, Dwave, and you can buy a quantum computer. They have done an enormous amount of engineering to make this work. See all this apparatus on the left here? That's refrigeration, most of it. The chip is the tiny little bit at the bottom. The rest of it's electromagnetic shielding, trying to get it down to millikelvin. And indeed, you can actually use this in the cloud at the moment. The only thing I would say is this is just a different quantum principle. It's a thing called adiabatic quantum expansion. So, and that's a whole different talk. So it's not what most people talk of as quantum computers. Having said that, Google, NASA, the Navy, they've all given them $10, $20 million, and indeed Google are now reckon that they can improve their searches using this technology by 100 million times. So if you read our paper, we've got the references in there to that. But let's go back to the sorts we're talking about today. First type of technology, linear ion traps. Basically, you suspend an ion between some electrodes, you hit it with a laser, you excite the energy levels, and you can control that. You can measure and control those energy levels, which can be qubits, as I mentioned before. Now, when you look at these, the sort of the original ones, oops, done it again. The original ones are, that's about the size of a couple of 10-pence pieces. The good thing about it is the results are optical, so you can read them optically. But this doesn't look much like a computer or anything that you could really use. And the best we've really got is about 7 qubits. There's 5 qubits running regularly, 7 qubits have been running. But linear ion traps, it turns out, can be re-engineered down to something much smaller. And only a couple of months ago, the guys in Zurich, they came up with this, which is ion traps on a board. So all of a sudden, it's starting to look a lot more chip-like again. So this is running, I think this might have been running 12 qubits, but I think 7 regularly. And indeed, the thing we'll come on to in a minute, Shor's algorithm, they were running that on this. So you can start to see, just as with going from those valves all the way down to transistors and getting more and more on a chip, we can start to miniaturize these things, and it is happening. It is actually happening. The other form of quantum computing that's a lot of work's been done on, the guys at Bristol are doing a lot on this, optical qubits. Turns out photons, you can when you go to the cinema and you've got polarized lenses and you've vertically, horizontally polarized, well, those are quantum states. And actually, you can use polarizers and all the rest of it to create all sorts of different quantum gates. And they've been doing it on single chips. So you have a Hadamard gate, you have a pi phase gate. These are all basically passing them through different kinds of polarizers. It's all on a bench. But what they're actually doing, if anybody's played with optical benches, you'll kind of recognize the equipment. But what they've done is they're just starting to squeeze all of that onto a single chip as well. So you've got basically photons on a chip, all rushing around, all doing quantum computing. And they have, again, they've managed to produce most of the types of gates on there. But the one that's really used most is what's based on what's called Josephson junctions. Don't want to go into what a Josephson junction is, except that the quantum property here is it's a superconducting circuit, and the current can go around anticlockwise or clockwise. And those are quantum properties. So whether it's going around anticlockwise or clockwise is its quantum state. And I know it sounds bizarre, but it can be doing both at once, right up to the point you measure it. And you can do all sorts of things like you can apply voltages to it to control it and measure it, etc. There are different types of things you can. Most of them use the charge that's on it. You can get what's called flux qubits. They're measuring, you've got a current going around in a circle. Guess what? It produces a magnetic field. You can measure that as well. So there are different ways you can measure and control this, but basically they're all using this same little bit of technology. And in practice, they look like that. So they're about 2 micrometers at the moment. They're teeny-weeny things, but there's basically that D-Wave computer I mentioned is also using these. So you've got current running one way, current running the other way. You don't know which. It's either 0 or 1. And that's actually when you build them a chip, that's a 4-qubit. This must be, gosh, this is 4 years old now, to show you how the technology has moved on. That was 4 qubits on a chip using Josephson junctions, and that was 2012. They did actually run Shor's algorithm on that as well. So you're all saying, right, well, when can I have one then? That was back in 2012. It's at this point that there is a little bit of reality has to come in. And if anybody knows Gartner, I don't know if you read Gartner's technology cycle, they have this hype cycle. Every year when I read their hype cycle, quantum computing is always more than 10 years away. I think that's because it always has been more than 10 years away, but it's not true anymore. Here's one I prepared earlier. This is one I actually have been using. It's a 5-qubit processor. I don't have it in my lab or my office. It's actually on the other side of the Atlantic, but I can get to it through the wonders of the internet. I can program it. In fact, I build very simple circuits for it just to test things out, and I built one just for today, which is about playing forward card Monty. If anybody remembers back to those early chips, the first thing I ever did with the 4004 was actually get it to play a forward card Monty. So here we are, and we've got 4-card Monty. You know the thing, it's find the queen. You've got 4 possible places. Let's call them 0, 0 through to 1, 1. We know the queen's at 1, 1. You tell the computer, right, sort those and tell me where the queen is. Now, if you just randomly guessed, it's a 1 in 4 chance. If you've got a fast sort algorithm, it's about 1 in 2.25. But the quantum computer, when you run it, gets it right first time. If you use this algorithm, this is called Grover's algorithm. It's one of the other famous quantum algorithms. This is my Grover's algorithm anyway. So I set it up, and that's how you set it up. You just put it together with gates on a circuit diagram. You fire it off. It comes back the result. And the result was as expected. It finds it first time, every time, at position 1, 1. Well, sort of. You'll notice, if you look very hard, that's just one run. You run it 1,024 times, and this is part of the problem with quantum computing. It's probabilistic. Unlike conventional computing, it produces the right answer probably. So most of the time, about 80% of the time, I was getting the right answer. But a significant proportion of the time, it was telling me with absolute confidence that it was somewhere else. And this all comes back to the fact that you're getting this wave-like interference of probabilities, and because they're probabilities, you can't get an absolute answer out of it. Bear that in mind. just for anybody who's interested, I mean, this is under the hood, and my little program down the side is, as you can see, it looks very assembler-like. But we were down at 14 millikelvin there. So the technical term is chuffing cold. So that is refrigeration like you've never seen before. To get this to actually work and run that program, it has to be extremely cold and no electromagnetic interference. Okay, so let's suppose you can have one. What's the problem? Well, this is where you need to be careful what you wish for. You all know that it's very easy to compute some things one way, but very hard to compute them the other way. So when you go into quantum cryptography, when you start talking about Shor's algorithm and breaking cryptography with quantum computers, 15 is a number that always comes up. Modern computing, take RSA for example, depends on the fact that you've got a number which is a combination, it's the multiple of two prime numbers. This is the simplest you can get. 3 and 5 makes 15. 3 times 5 equals 15 very quick. Trying to work out what the prime components are of 15 takes longer. Doesn't seem to take longer at this size, but obviously as you get larger and larger it does. And if you look at RSA, we've got, I think we can still break something like a 600-bit RSA in probably about 3 months. This is using classical computers, using a thing called the general number field sieve, which is the fastest we have at the moment for factoring numbers. So turning that 15 into the 3 and 5. However, you only need to get to about 700, and it's never been done. It's never, ever been done. And you know, what's really interesting, in the same way that there is a Moore's law, there's also a kind of a law to do with prime numbers. Ever since we've had computers available to people in general, people have been coming up with larger and larger and larger prime numbers. And so people will simply say, oh, well, you know, let's suppose you can crack 700 bits in 3 months. I'll just make it 1,400 bits or 2,000 bits or whatever. So they just have bigger, and there are plenty to choose from. So everybody is sort of resting happy, except that Peter Shor, who's my idea of a mad scientist, he just looks fantastic. He, back in 1996, worked out a way of using quantum computers to do factoring in polynomial time. So rather than exponential time, he worked out how to do it in polynomial time. And that's what I want to try and talk a little bit about now. To explain, we have known how to factor numbers like 15 into 3 and 5 for a long time. 1760, Euler, who one of the many geniuses, you think, how did he come up with those things in those days? He pointed out that if you have a large number n, which is a composite of two prime numbers put together, there is a function that you can construct, provided you choose the numbers in certain ways, where if you can work out that function, x to the a mod n, back into modular arithmetic now, it turns out that that has a period r, which, with a bit of number theory, and using an even older algorithm to calculate what's called the GCD, the greatest common denominator. The greatest common denominator is done using a Euclidean algorithm, of all things. He worked out, we know that if you can determine r, the period r, you can actually then work out what p and or q is, the two components. So you put it together, being a good computer scientist, I drew myself a flow diagram, and all of that, that's Shor's algorithm, because it's not actually Shor's algorithm, it's Euler's algorithm. The big thing is, you can run that in Excel. I've got an Excel sheet that'll do it for you if you like. But what Peter said was, I could do this in Excel, didn't have Excel at the time. Working out this period is going to take a long time, except that he knew that he and a number of others had come up with a thing called the quantum Fourier transform, which is a way of rapidly finding out the period or the frequency of a function. And so when people talk about Shor's algorithm, what they're really saying is it's that, which is a classic algorithm, but that bit in the middle about determining the period, that's the only bit that's quantumized, if that's a real word. That's the bit you run on the quantum computer. you can, I don't want to take you through it because we don't have time, but you can actually go through this by hand for 15. 11's co-prime. You divide 11 by 15 because we're doing modular maths again. You take the remainder. You square. You quadruple. Not quadruple. You power 3, power 4, etc. And you find that it goes 11, 1, 11, 1, 11, 1. It's got a period of 2. You then work through the number theory as before, and sure enough, out pops 5 and 3. And you just have to trust me, as you get bigger and bigger, that works for all of them. So, how does that look if you put it into a quantum computer? Well, those diagrams I was showing you before, those circuits I was putting together, the Grove's algorithm, this is those gates put together to produce Shor's algorithm, or rather, it's the period finding element of the algorithm. It's based on something that's more fundamental. This wasn't actually how Shor formulated it in the first place. This is kind of how a number of people, including me, Bill and I, have actually done it in our paper. We're using a thing called the phase estimation algorithm, for reasons I'll explain in a second. The phase estimation algorithm is for any signal processors in the audience. It basically says, if I've got a function that's e to the 2 pi I phi, you can work out what that phase is. And if you've got your function, which we know from before was that rotating function, that modular function, and you can get one set of qubits multiplied by that function, then by using a thing called the reverse, the inverse quantum Fourier transform, you get the answer. But there is a small problem, and that is that the phase estimation algorithm is only as long as the number of qubits you have. So at the moment, obviously, we're relatively limited. But as we get more and more qubits, you find that some of the maths falls nicely into place in that repeating function, if you write it out as a series, it just suddenly becomes a Fourier transform, effectively, which if you take a Fourier series, rather, if you take the inverse Fourier transform of it, gives you the phase, which happens to be the very number you're looking for, that period that you're looking for. One of the problems is that little function u of s there is dependent on r, so you get this sort of circular argument. But it turns out there's a neat little trick where the sum of that over all the values of r equals 1. So what you do in the computer is you never bother about that second register. You don't know what the value is, and then you never care. You just assume it's working. You trust the maths that it's working. What you actually measure is the first register, which has been controlled by the second register. And because they all exist at once, when you measure it, that's how the answer pops out. And there's the math, if anybody's interested. The bit that gets most people confused, and it was another one of those little twists in Shor's algorithm that people say, well, hold on a minute, you get down, let's step 3 there. That's probably the crucial one. You've taken your inverse Fourier transform. You've still got a whole series of possible values there. You measure and you get 1, and it'll be a random selection from all the possible answers. So how does that tell you anything? Well, it turns out that if you've got any fraction, s over r in this case, and we're interested in r, there is another method, age-old method, of working out a good candidate for r. You can work out what r probably is. And once you've got that candidate, you can very quickly go back and say, was that the right answer? And that's basically how it works. You get candidates, you try it. If it's the right answer, you carry on. You've got the answer. If not, you go back and try again, because it's so fast. But the point about this is that all of these calculations, those sums there, are all being done, all being computed. That function, it's all being done in parallel. It's all being done at once. Whereas in a conventional computer, you'd have to go through every possible value, which, as you get to those much larger prime numbers, is just going to be unworkable. I won't take you through that. If anybody is interested in continuing fractions, I don't have time to go into it here. There is a link there. That's that funny little trick at the end. Continuing fractions, we've known about it for years. I still don't fully understand it myself. I tried to write it up in the paper, and it made my head hurt. But it really is, I mean, it's amazing how Peter thought of this. I just don't know. He saw these two things together and thought, I know what. In practice, this is what Shor's algorithm looks like when you do draw it up in a circuit diagram. It gets big. So that's just for 4-bit numbers. So you can see we're going to need some very large numbers. And you can actually start to quantify that speed up. This will be the bit you're probably interested in. Let's suppose we have a k-bit number. You can see the order of magnitude that it's going to take for the general number sieve, and you can see that it's basically a cube law on the quantum computer, and that you're going to need 5k plus 1 qubits to do it. So you can start to see that your k, you're going to need at least 5 times the number of bits in qubits in order to get the answers, hence the reason it's still not practical. And you can start to draw that out. This is my little calculation. And up to sort of 100 or so bits, actually the general number field sieve is faster than Shor's algorithm, but what then happens is that you go to hundreds of bits and Shor's algorithm doesn't break into a sweat. The general number field sieve just increases exponentially. So the general number field sieve on conventional computers is just like that traveling salesman problem. It increases exponentially, whereas Shor's doesn't. It's in polynomial time, it increases linearly. So you can have as many 1,000 bits as you want in your prime number composite. Shor's algorithm will still deal with it. There are some people that are still arguing about how you scale it, etc., but the theory is pretty much all there. And if you want to play for it yourself, there's a thing called the quantum playground. If you really want to understand it, I would thoroughly recommend the quantum playground, of which Shor's algorithm has been added to it. But this is where we come up with a big but. There is an inconvenient truth. The whole point about this afternoon is that Shor's algorithm kills stone dead when it's working. RSA, because that depends on prime numbers. Shor developed another algorithm which is very similar. You can formulate it out of that phase estimation algorithm again, where you can work out discrete logarithm problems, which is another issue to do with elliptic cryptography. But there is a notable lack of new quantum algorithms. One of the things we've said in the paper is, look, the quantum algorithms that have been derived so far, there are some quantum simulations, which is what it was all about in the first place. There's Grover's algorithm, but Grover's algorithm, it doesn't speed things up exponentially like Shor's algorithm. And then you have Shor's algorithm and the discrete logarithm algorithm, all of which, it turns out, are just one set of problems. They're what's called the hidden subset problem. You can formulate it as variations on one problem. There isn't anything else. So as far as we know, it should be possible to create crypto systems that are not attackable by quantum computers. All you need to make sure of is that it's not using a mathematical problem that is part of the hidden subset problem. And sure enough, it turns out there are quite a few of those out there. Most people will have heard of lattice cryptography, etc. Again, we go through the paper, we do a review of the different candidates. My personal favorite is a thing called learning with errors. I think that's going to be probably the winner. But again, predictions. Oops. And that's really where we need to hand over to Bill, who I think at some point is going to talk about some of these candidates.
Questions? No questions?
Oh, yeah.
Questions. I'm sure everybody here found that thoroughly fascinating.
I think, as I apologise, it's extremely quick.
I think Schrödinger's cat was only mentioned once,
yes.
Very briefly. Please, who has some questions?
Everybody understood? Really
one question at the back, yes.
When you look at these qubits and the hardware that's needed to interrogate, what sort of power, electrical power, is needed to run that equipment?
It's interesting because you go back to the old ones. I've mentioned that ENIAC, for example, it's 150 kilowatts to run it. I mean, actually, most of the power is not for the processor, it's all for the refrigeration, etc. Which is one of the reasons why it is taking kilowatts of power to run things like that. Interestingly, one of the interesting things, I didn't mention it, I mentioned it right at the beginning, if people were listening, that I mentioned that conventional logic gates are irreversible. Quantum logic gates are not, they're reversible. Now, Landau did his work at IBM in the 1960s that showed that some of the heat that's produced in computers is because it's an irreversible process. Quantum computers don't have that problem. So theoretically, quantum computers should be efficient. But the problem is engineering it to stop them falling out of superposition. You need all this gubbins around it.
Question? Yeah. Thanks.
So,
Yes.
is the progress in quantum computing following something similar to Moore's law?
No, it's kind of bumping along the bottom. It has been bumping along the bottom. And some of that is because there's been no imperative, I think. All of a sudden, people have recognized that the potential, if you like. So suddenly money's going into it. I mean, the UK government's putting in nearly £300 million alone. The US government, something similar. We've got NASA, Google, people like that putting tens of millions into this. So suddenly in the last probably when did I do that original lecture, Bill? Must have been 3 years ago. In that period of time, we've suddenly seen things appear. When I did that lecture originally, they didn't exist. The theory was all there, but there wasn't one you could play with. Now there is. And we've got I use a 5-qubit processor with IBM. Google have said they believe they'll have a 50-qubit processor by next year, or the end of next year. So yeah, it's kind of, I think what you're going to see is something not dissimilar starting to happen.
Do we have a question at the back? Thank you.
Yeah, I was just wanting to confirm if the success of quantum computing depends on not being able to explain or to observe the simultaneous states of the matter.
Sorry, you mean it's... actually, that's a good point. I didn't make a good point here. One of the reasons there isn't suddenly a massive plethora of different algorithms, and, oops, let me go to there, is because because you can only get one answer at any one time. Yep. Even though all the answers are in there, they're locked in the quantum computer. What matters is designing an algorithm that when you get that one answer, it's the right answer, or it's an answer you can use. As it happens, for the reasons I was talking about, Shor's algorithm does do that. You can use the funny fractions algorithm to tease the answer out. But most things, you don't get this, there isn't this, and it's the inconvenient truth really, that sort of, it's the elephant in the room, that quantum computers are not some general speed up. They're not like a leap forward in processor power. They will be of use only for certain types of algorithms. Grover's algorithm is a fast search engine, and that will work very fast. You can see why Google's interested in that. But for things like cryptography, no. It's not just going to suddenly render it all useless by speeding up all possible cracking algorithms. It's only very specific, and finding those specific algorithms is very difficult. Just think about it, in the last 20 years we've had hardly any others. They're all derivatives of the same thing. And they all come back to the same primitive as well, in this particular case, which is that quantum Fourier transform, which, if anybody has done any signal processing, I mentioned all the way through this, quantum computing is all based on interference, basically, wave patterns. That's why the quantum Fourier transform is so good, because the whole point about quantum series and quantum Fourier transforms is it's all about waves. It's all about decomposing waves. And that's effectively what quantum computers do. So we've got to change from Shor. Because of Shor, we've got to change from RSA and prime number-based cryptography. But it's not the end of cryptography. That's how we titled our paper. It's not the end of cryptography as we know it. And it's also very interesting that symmetric cryptography as well, it doesn't. People say, well, what about AES, for example? AES, you could say, well, I could use Grover's algorithm, just brute force it. I'll guess all the keys, and it'll be 100 million times faster. It turns out you only need to double the length of the key, and you spoil their party. And there are much easier ways of cracking AES, as Owen's going to show us, I think. So people are not really looking to quantum computer for that. So yeah, it's a complicated answer, but it's one of those things where they're not the answer to everything, but they make life very difficult in certain dimensions.
Fantastic. I have an observation, I think, that material science, high temperature quantum effect materials will have a big impact in the future.
Well, and we're starting to see some interest. As I mentioned, that topological quantum computing, one of the really interesting things is that people have said, if we find a way of producing qubits that we can process at room temperature, that will suddenly, it will be a different ballgame. And there is some evidence that that's starting to happen. I think the first will be very much like these monolithic things that require rooms with refrigeration, etc. But do remember, when I started in computing, that's what conventional computers looked like. We had chilled. I installed the last IBM 3090 in the UK, and we had chilled water pipes coming in and great big plant. It isn't the laptops you all love and cherish today. We had great big machines. So really, it's just going to go through the same evolution, and as quickly, I think.
Thank you very much indeed. Please put your hands together. Professor Woodward. Thank you very much indeed. Thank you.